Hi, everybody. Welcome to this talk on network science. I would like first to thank the organizers of LawCG for inviting me. I thank you very much. And this is a short summary of my talk. I selected here a few aspects of network science that I particularly like. I hope you enjoy it too. And always remembering that this subject is very large and this is just a small sample of everything that there is to study in this subject. All right, so let's start with the small world property. This property refers to the fact, to this idea, that with 6 degrees of separation, you can reach any person in the world from any other person. So, for instance, in this picture, you have a degree of separation between Peter and Jane, and then another one between Jane and Ralph and Sarah. So, between Peter and Sarah, you can say you have 3 degrees of separation. Well, the idea being then that with 6 degrees you can reach anybody in the world. Uh, this has a long history from the beginning of the 20th century. First mention of this is in works by Hungarian writer Karinthi, 1929. A couple decades later, two people, mathematician Cohen and political science de Solapol, wrote the first mathematical analysis of the subject. It was published in 1978, but was widely circulated at least 20 years prior, since 1958. So much so that social psychologist Milgram performed an actual experiment with that. He mailed questionnaires to random people, asking them to follow instructions, try to contact uh, his acquaintances until reaching another random person. And not everybody replied, but from the ones who did, he found a mean of 5.2 degrees of separation. Okay, all this was in the academic setting, but in 1991, a Broadway play called 6 Degrees of Separation by John Ware uh, started and was very successful, and this helped spread the idea through the outside of academia to all levels of society. Later on the same decade, two physicists, Watts and Strogatz, wrote a Nature paper showing how a few changes in a highly regular graph, which does not have the property, are enough to make it small world. And then a year later, another group of physicists, João, Albert, and Barabasi, published another Nature paper estimating degrees of separation for the World Wide Web, which is documents now instead of people. And it's a much bigger network, so they found 19 degrees. They estimated 19 degrees of separation. And more recently, in 2011, a team inside Facebook used their social network to estimate 4.7 as the mean separation for their users. Okay, and what is the small world property? Usually, we think that a network is a small world when the average distance, denoted here by d between angle brackets, is proportional to the logarithm of the size of the network, the number of nodes. Okay, so in random networks, you have this property. Average distance is proportional to log n divided by log of average degree. So for us, K is the degree. So angle brackets K is the average degree. However, in regular graphs, like the L-dimensional lattices, for instance, uh, this does not happen. They are not small world because the average distance is proportional to a power of n. And cycle powers also, the average distance is proportional to n itself, modulated by a factor involving the degree. In this case, the degree is depends on a parameter k. But okay, it's not small word either. So regular graphs are not small word in general. And then this is a summary of the work by Watts and Strogatz in their 1998 Nature paper. So they departed from a sparse cycle power. Okay, so n is big and k is small. And then with probability p, they changed a few links. So a link connecting two nodes will connect one of them to some other node. So switch a few links. And then they realized that by doing that, as p increases, you see a dramatic drop in the average distance. So here we have a graph with a logarithmic scale on p, and you see that already with p equal to 0.001, you are about half the original average distance. And with p equal to 0.1, you have 1/10 of your original distance. So this was an interesting result. But what happens with real networks, networks that exist in real life? For instance, here we have 10 representative networks of what you can find in real life. The internet routers, computers that connect to each other and build what we know as the internet. The World Wide Web documents, with links being one page linking to another. Power grid stations in the US, connected by cables and transmitting energy. Mobile phone calls, email messages, science collaboration, which is a network composed of all authors of scientific papers and links between authors that co-authored at least one paper. Paper citations, it's more or less like the World Wide Web, but instead of hyperlinks, you have one paper citing another. Actor co-starring is more or less like science collaboration, but it's actors co-starring the same production. And the last two are biological networks. The E. coli metabolism. E. coli is a bacterium very, very used in biological experiments in all labs all over the world. And the metabolism is a network where the nodes are compounds that exist in the E. coli cell. And there is a link between one compound to another if inside the cell there is a chemical reaction that transforms the first one into the second one. So it's a directed network with metabolites and chemical reactions as links. Finally, the protein interaction network for any species or living organism is the nodes are all the proteins that exist in this organism cell, and the interaction is the link is if the two proteins interact in some fashion. For instance, they can join and produce together some kind of structure like a cell membrane or something like that. Or one can serve as an enzyme and perhaps block, modify, or somehow interfere with the expression of the other one. So interaction here is interpreted in a very broad sense. Anyway, In most of these networks, if you compute the average distance and then log n divided by log average degree, you see a neat correspondence. Okay, uh, the so it's the same ballpark. Sometimes one of them is like 2 or 3 times the other, but it's never beyond that. So the agreement is very good. We can say that all these networks are small world. All right, let's talk now about scale-free networks. And the study of scale-free networks starts with a question. Is the World Wide Web a random network? 20 years ago, people didn't know, or maybe 22 years ago, people didn't know the answer to this question. The World Wide Web might well be a random network. After all, both are small world. And random networks, however, have been studied for quite some time, since around the middle of the 20th century, by Erdős and Renyi, who published a series of papers in the 1950s, going up to the 1960s, or maybe they started in the 1960s, perhaps 59, something like that. Yeah, I think that's it. And also Gilbert also published papers on random networks. The difference is that Erdős and Renyi used what's called the GNL model, in which the input is n, the number of nodes, and l, the number of links, and then you select at random a graph with n nodes and l links. Whereas Gilbert used another more or less equivalent model, which is you select n, the number of nodes, and p, the probability of having an edge, any one of the total of possible edges, and all edges will exist with the same probability p. Gilbert model is easier to work with, so it became recently it's almost universally used, and we're going to use it here too. But okay, so what do we know about random networks from the work of these people and others who worked on the subject? Well, we know quite a few. We know quite a few pieces of information. The first thing we know is the average degree, which is roughly n times p. The average number of edges is also p times the total number of possible edges. The degree distribution, we have a closed form, it's just a binomial distribution, but we also have a Poisson form, which is a good approximation for the binomial form when n is large and the product np is moderate. Np, which is approximately the average degree, is moderate. In this case, you can approximate by this Poisson formula, which doesn't involve n, which is a big gain. Only involves the average degree, the product, and np. Okay. We also know what happens with the connectivity of the network as the average degree varies from 0 to its maximum possible value. So here is a picture showing the size of the giant component, which by definition is the largest component of the network as the average degree varies. So if you have a very small k, k between 0 and 1, average k between 0 and 1, then your network is just a scattered collection of disconnected components, most of them being, almost all of them being trees. Okay? So the average, the size of the giant component is negligible compared to the size of the network, so we have 0 there in the graph. And then something suddenly happens when the average degree is 1. Then we start to have a largest component, the giant component. And it starts to grow and grows very fast until it encompasses a finite fraction of all the nodes when average degree is above log n. So this is a very celebrated result and very useful for us. Okay, so given that, how does that agree with the World Wide Web? Well, starting with the degree distribution, you can see that they don't match at all. In green here, you have the Poisson law. So the World Wide Web is a directed network. So you can think of the degree distribution, the in degrees and the out degrees. So we have a graph here for both. And in both cases, you see the gray dots represent data gathered from the network itself. And then in purple, you have the straight line fitting this distribution. And since this is a log-log plot, a straight line means a power law. So the probability of having a node of a certain degree is proportional to a power of this degree, a negative power, which is a straight line in log-log plot. And you see that the Poisson distribution is not a good fit for the gray nodes. So this shows there are other considerations too, but this definitely shows that the World Wide Web is not a random network. And this prompted the definition of scale-free networks. Scale-free networks are networks for which the degree distribution follows a power law. So P of k is proportional to negative power of k, modulated by an exponent gamma. Okay? And why it's called scale-free? Because it has no scale, in a sense. The first moment exists, but as n tends to infinity, the second moment diverges. So you can have an average degree, the first moment, but if you try to compute the standard deviation of the degree, this thing tends to infinity as n grows. So this is noticeable even in the finite setting. For instance, World Wide Web is a finite network. But if you compute its average degree, you will find 4.6 plus or minus more than 1500. So when you draw a random node from this network, you have no idea of what its degree is going to be. It can be almost anything, from the minimum to the maximum. So this is in opposition to what happens in a random network, for instance, where most nodes have a degree close to the average. Here, they don't. All right. And here we have the 10 networks that we talked about before again, and showing that most of them are scale-free networks. The ones that are undirected have power law distribution both in the in degree and the out degree. And the undirected ones have also a gamma that can be estimated. The only exception is the power grid stations, who follow an exponential degree distribution. It's not scale-free. All right, what's the implications of being scale-free? The existence of hubs, nodes with very high degree, much higher than the average, which provides robustness against random failure. If you lose a few nodes, the hubs make sure the rest is connected. And also means vulnerability to attacks, because if someone wants to disconnect the network, it can go after the hubs. And also a small word property, because the hubs connect everyone very fast. With a few hops, you reach any node from any other node, which has implications for fast spreading phenomena, as we'll see later on in this talk. All right. Let's talk a little bit about degree correlations. In some networks, for instance, in the celebrity network, uh, hubs have a tendency to link to other hubs, or in general, nodes have a tendency to link to nodes of the same degree. So this is what's called degree correlations. Okay? And according to the degree correlations, we can have three types of networks. Networks where hubs tend to link to other hubs, and networks where hubs tend to link to nodes of small degree, and vice versa. Small degree nodes tend to link to hubs and not among themselves. And also there is a neutral kind where you don't notice any particular bias. So we have three ways of measuring this kind of behavior. One is the degree correlation matrix, the other is the degree correlation function, and the other is the degree correlation coefficient, going from high memory to low memory needed to store the information. Okay, for the degree correlation matrix, it's you compute Eij as the probability of finding nodes with degrees I and j at the two ends of a randomly selected link. So assortative networks, where nodes tend to link to others of the same degree, you'll find a lot of concentration in the main diagonal. A neutral network doesn't show preference for any diagonal. And in this assortative network, you'll find concentration of this probability on the secondary diagonal. Okay. Now, for the degree correlation function, you build a function called KNN, which is the average degree of the neighbors of all degree k nodes. So if you plot this graph, this function, and you find more or less a straight line going upwards, that's an assortative network. If you have a straight line, a horizontal, more or less horizontal line, you have a neutral network, as exemplified here by the power grid. And in this assortative network, you'll find a straight line going down, as in the metabolic network here. All right. And finally, we have the degree correlation coefficient, which is based on the deviation of Ejk, defined as the matrix as we saw, as compared to what happens in a random network of the same characteristics. Okay? So this coefficient resembles somehow the Pearson correlation coefficient in statistics, and also shares with the Pearson coefficient this property of being always between -1 and 1. And if R is positive, you have an assortative network. And if R is negative, you have a disassortative network. Okay, and R near 0, it's a neutral network. Now, computing this correlation coefficient in some of the real networks, we find that usually social networks are assortative, and biological and technological networks are disassortative. Why is that? Nobody knows, but has been observed in practice. Okay, let's talk a little bit now about network robustness. And when we say robustness, we are referring specifically to the fact that how many nodes you have to remove to disconnect the network. And if you remove nodes at random, we are testing the resiliency of the robustness of our network against random failures. And if we can choose the nodes to remove, then we are talking about planned attacks. Okay, so let's see how networks fare uh, according to these things. Okay, the existence of a giant component for random networks we just saw in the previous slide. It depends on the average degree. If it's bigger than 1, you have a giant component. If not, you don't. But scale-free networks are not random. However, Molloy and Reed published a paper a few decades ago giving a condition for a giant component for random networks with a specified degree distribution, like we have for scale-free networks. And then the condition becomes, okay, the threshold now is 2 instead of 1, and what you have to measure is the average square degree divided by the average degree. If that's less than 2, you have a bunch of small components, most of them trees. And if this is bigger than 2, you have a giant component. So this is our criteria to see if a network is how it withstands failure. Okay, and this is useful in particular when we study spreading phenomena. Spreading phenomena are diseases, of course, but not only diseases. For instance, rumor spreading, they follow similar patterns, or innovation diffusion. Someone has an idea for a new product, and this idea is used as it is used, is copied, people like it, it's being used more and more. And so all this is studied under the spreading phenomena uh, idea. Okay, so the classical epidemic modeling studies 3 models. The SI model, which are seen here, but there are 2 more that we're going to see in the next slides. So this is the simplest model, where you have a population of susceptible individuals, which are healthy, and they can get infected and become sick. And once they become sick, they don't recover. So some diseases are like that. You get the disease, you never. There's no cure. But also spreading of information follows this model, because once you get a piece of information, you got it. There's no way to undo that. So there are differential equations modeling the fraction of infected individuals and the fraction of susceptible individuals. And to become infected, it depends on the derivative of the fraction of infected individuals over time, depends on some rate, constant rate of infection, beta, depends also on the average degree of the network that's underlying this infection, which in the classical modeling is taken to be a random network. Okay, and then it also depends on I and S, because the more infected people you have, the more likely to infect more people, and also in the number of susceptible individuals, because the more susceptible you have, they can get sick. Okay. The other model is the SIS model, where you do have recovery. So you are healthy, you get the disease, but then you can recover. But when you recover, you go back to the susceptible state, which means you can get the disease again. Okay? So the common cold, for instance, follows this pattern, and a number of other diseases. And here the equations become just a little bit more complicated, with an extra term measuring, accounting for the fact that some of the infected individuals go back to the susceptible state. And finally, the most complex model, which is the SIR model, in which you are healthy, you get the disease, and then when you become cured, you don't get the disease again. So you are removed from the pool of susceptible individuals, and you don't get the disease anymore. Or if you die, you also are removed from the pool. Okay, so in this case, the equations become a little bit more complex. There are three compartments, three types of people now to worry about. And to summarize what happens in each one of these models, okay, they all start with an exponential phase where the number of infected individuals shown here in function of time grows exponentially. Okay, so all three models, they have a starting phase where the disease spreads exponentially. And then in the SI model, this grows until it reaches the entire population, because there's no way to not to be cured, so everybody will be eventually infected. In the SIS model, depending on the relationship between infection rate and recovery rate, you tend to reach an endemic situation where you have a constant fraction of the population infected uh, all the time. You have this constant fraction of the population infected. And in the SIR model, in the end, the tendency is to have zero people infected. Everybody is back to susceptible or removed. Okay, but that classical modeling relies on the fact that the network, the underlying network, is random, which is not the case for real networks. So, what we need is network epidemic modeling, taking into account that most underlying networks where the disease or the news are spreading are scale free. So, when you have this situation, the continuum equations become a lot more complicated, because actually now the way the researchers deal with that is they have a family of equations instead of one equation. A family of one equation for each value of k, the degree of a node. So degree k nodes, each class of degree k nodes, for each value of k, you have a different continuum equation to deal with that. Okay, and they're a little bit more difficult to solve, but in the end, you can draw conclusions about the epidemic conditions. So these epidemic conditions are conditions that will tell you if the disease will spread and dominate a giant component of the network or not. Okay, so this combines the network robustness results that we saw with these differential equations, and we conclude that in the SI model, uh, just having a positive infection rate is enough for you to have everybody contaminated. So a big, giant component will always exist as long as beta is positive. Now, for the SIS and the SIR model, the conclusions are the epidemic condition depends on the rate, infection, the ratio of infection rate divided by recovery rate, and that has to be bigger than average k over average k squared. But have bear in mind that for scale-free networks, uh, the average of k squared is much, much bigger than the average of k. So the number you have in the right-hand side is very, very small. So it doesn't take uh, uh, much for beta over mu to be bigger than that and for you to have an epidemic condition. Okay, so scale-free networks make the spreading phenomena much, much faster. Okay, that's the take-home lesson. This is just, I just added this slide because this was from the network science book which was written 4 years ago, but it's tremendously current, because look at that, face masks, gloves, hand washing, everything that we're doing right now with the COVID-19 pandemic. Quarantine patients, close schools, limit to public spaces. And also, there are some interesting results about vaccination. So, vaccinations help in two fronts because they permanently remove vaccinated nodes from the population being considered, and because they reduce the spreading rate. Now, what's the smartest way of immunize a population? Of course, if you target the hubs, that will be the best thing because they are responsible for the fastest transmission. But how to find hubs? Sometimes it's difficult to find hubs. Like in a social network, who are the people who have most contacts? It's sometimes not easy to find. But there is a strategy you can use using the friendship paradox. The friendship paradox is the fact that, on average, the neighbors of a node have higher degree than the node itself. So this leads to a strategy which is selecting a fraction of the population and then selecting a neighbor of each one of these guys to be vaccinated. Okay? You do that, that we call selective immunization. Uh, Here's what results. So here we have a graph of gamma, which is the power of the scale-free network. This was simulation done with many scale-free networks of varying gammas. And GC is a fraction of people you have to immunize to stop the epidemic from reaching a giant component, okay, from generating a giant component. So you see that with random vaccination, it's hard to do that. With the high gamma, like 3.5, you still need to immunize like 50% of the population. But for selective immunization, it's barely above 30%, so it's really effective. Okay. All right. I guess that's what I had to say to you now, and the rest is just a list of references that I used in the talk. Feel free to consult them afterwards. So I thank you very much and hope you enjoyed. Bye bye.